Chapter 3 of History of Chemistry, Volume 2 by Sir Edward Thorp. This LibriVox recording is in the public domain. The inactive elements, radium and radioactivity. Argon, helium, krypton, neon, and xenon belong to the group of the so-called inactive elements and constitute what are known as the rare gases of the atmosphere. The existence of these bodies is of great theoretical value, and few discoveries of recent times have excited more interest and curiosity. 20 years ago it was generally assumed that practically all that was to be known concerning the composition of atmospheric air had been ascertained. Priestley and Cavendish had recognized that it was mainly composed of oxygen and nitrogen, and Cavendish had definitely stated that these gases are present in practically constant proportion, independent of season, climate, or locality. Thénard, Saussure, and others had determined the limits of variation in the amount of carbon dioxide. Bunsen and Regnault had established that the quantities of oxygen and nitrogen are subject to slight alteration, the extent of which could be readily determined by the exact eudiometric processes they had devised. Lastly, it was proved beyond a doubt that the gases of the atmosphere are simply mechanically mixed and can be separated by a variety of physical methods. In fact, of no single subject could it be more confidently assumed that finality of knowledge had apparently been reached. In 1892, in the course of a series of determinations of the densities of the common gases, Lord Rayleigh found that the density of nitrogen obtained from the air was slightly greater than the density of that gas prepared by the decomposition of ammonia and of nitric acid, the difference in weight being about 1 part in 200, an amount far greater than could be accounted for by errors in weighing. Various suppositions were made in explanation of the discrepancy, but these, when tested, were found not to account for the facts. By heating the atmospheric nitrogen with metallic magnesium, whereby the greater portion of the gas is absorbed to form the nitride, Sir William Ramsay found that the density of the residual gas was still further increased, which rendered it probable that the relatively high density of atmospheric nitrogen, as compared with that derived from ammonia, and as Lord Rayleigh found from other sources also, was due to the presence of a gaseous substance in the air of considerably greater density than nitrogen or oxygen. Lord Rayleigh also subjected atmospheric nitrogen mixed with oxygen to the electric discharge over a solution of caustic soda, in a manner similar to that already employed by Cavendish, and found also that the residual gas was considerably increased in density. At the Oxford meeting of the British Association in August 1894, the two investigators were in a position to announce that the discrepancy was actually due to the presence of a hitherto unknown gaseous constituent of atmospheric air, considerably more soluble in water than nitrogen, and to which, on account of its chemical inertness, the name of argon, from the Greek argon, idle, was given. By a special apparatus devised by Lord Rayleigh, in which a mixture of air and oxygen is submitted to an electric flame produced by a powerful, rapidly alternating current, considerable quantities of argon were separated from the air. It has also been found that by the use of metallic calcium, or a mixture of magnesium and lime, the atmospheric nitrogen is absorbed at a lower temperature and more rapidly than by magnesium alone. Argon has been found to exist in the gases from springs and mineral waters, notably in those of Bath, Cauteretz, Wildbad, and Harrogate. It has also been found in a meteorite, in the gas occluded in rock salt, and in the minerals malacone, uraninite, brugerite, etc. No animal or vegetable substance appears to contain it. It is present in atmospheric air to the extent of about 1% by volume. It is a colorless gas of an atomic weight of 39.9. 1 liter of it at the standard temperature and pressure weighs 1.7815 grams. Experiments made by the method of Kundt and Warburg, that is, by determining the ratio of the specific heats at constant pressure and constant volume by the velocity of sound in the gas, prove that argon, like mercury gas, is monatomic. This of itself indicates that argon is an element, since a monatomic compound is a contradiction in terms. The calculations from the experimental data presuppose that argon obeys the laws of Boyle and Dalton, which was found on trial to be the case. By the application of cold and pressure, argon can be liquefied. The liquid boils at -186.1 degrees and freezes at -187.9. The spectrum of the gas is exceedingly complicated, consisting of a great number of lines extending throughout the visible portion and far into the extreme red and ultraviolet. The color of the light emitted on sparking the gas changes with increase of temperature from a brilliant red to a bright blue, depending on the intensity of the discharge. All attempts to induce argon to enter into combination with other substances have failed. The methods of its preparation show that it does not combine with oxygen, although Troost and Ouvrard state that it unites with magnesium vapor. It forms no compounds with hydrogen, chlorine, phosphorus, sulfur, sodium, tellurium, etc. Even fluorine, probably the most generally active of the chemical elements, shows no tendency to unite with it. In 1888, Dr. Hillebrand of the U.S. Geological Survey, in examining a form of uraninite known as clevite, so named from the late Professor Kleve, found that on treatment with dilute sulfuric acid it gave off considerable quantities of a gas which was assumed to consist only of nitrogen, as it gave the spectroscopic reactions of that element. To test whether this gas contained argon, Ramsay in 1895 further examined it spectroscopically. After sparking it with oxygen in the presence of caustic soda solution, in the way already described, it gave no indications of argon. The main characteristic of its spectrum was a bright yellow line, known as D3, not coincident with that afforded by sodium, but identical in position with a line detected in the chromosphere during the solar eclipse of 1868, which line, on examination by Frankland and Lockyer, could not be ascribed to any known element. For this new element the name helium, from the Greek helios, the sun, had been suggested. This was the first occasion on which an element observed originally only in the sun was found to occur also on the earth. The presence of the new element in the gas from clevite was subsequently confirmed by Langlet, working in Kleve's laboratory. Helium is a monatomic gas having the atomic weight 4. It is less soluble in water than argon. Like argon, it shows no tendency to enter into chemical union with any other substance. It has been found in many minerals, particularly in those containing uranium and the so-called rare earth metals. It also occurs among the gases issuing from certain mineral springs, such as those of Bath and at Cauderetz in the Pyrenees, and also at Adano near Padua. The spectrum of helium contains, in addition to the characteristic yellow line, by which its presence has been recognized not only in the solar chromosphere, but also in certain of the fixed stars, 2 lines in the red and lines in the green, blue, and violet. The character of the light emitted by the spark discharge is modified by the intensity of the discharge in a manner similar to that of argon. It has been shown by Colley that its spectrum is altered by the presence of mercury vapor. It is the least refractive of all the gases. Helium was liquefied by Kamerlingh-Onnes in 1908. It forms a colorless liquid of specific gravity 0.154, boiling at -268.5, that is, 4.5 degrees above the absolute zero of temperature. Its critical temperature is about 5 degrees absolute, and its critical pressure above 2¼ atmospheres. The methods now in use for obtaining liquid air, referred to in a subsequent chapter, enable large quantities of that material to be obtained readily, and it was in investigating spectroscopically the residues left after volatilizing a quantity of liquid air that Ramsay and Travers in 1898 detected the existence of 2 new monatomic gaseous constituents of the air, which they named respectively krypton, from the Greek kryptos, hidden, and neon, from the Greek neos, new, the former heavier and the latter lighter than argon. By fractional distillation of the argon, simultaneously procured, a gas was obtained which in the spectroscope showed the characteristic lines of helium, previously recognized in atmospheric argon by Kaiser and Friedlander, together with a complicated spectrum consisting of a number of lines in the red, orange, and yellow due to the new element neon. On cooling this mixture to -252 degrees by means of liquid hydrogen, the neon solidified, while the helium remained gaseous and could thus be separated. Krypton was obtained from the residues left on the evaporation of a large quantity of liquid air. Mixed with the krypton was a third gaseous constituent of air, to which the name xenon, from the Greek xenos, the stranger, was given. The boiling point of krypton at atmospheric pressure was found to be -152 degrees, and its melting point -169 degrees. The boiling point of xenon was -109 degrees, and its melting point -140 degrees. Their critical temperatures were respectively -62.5 degrees and +14.7 degrees. Hence, xenon could be liquefied by a pressure a very little below the mean temperature of the air. Neon boils at -243 degrees and freezes at -253 degrees. They form colorless liquids freezing to ice-like solids. All of them, with the exception of argon, which is present to the extent of about 1 part in 107 parts of air, are contained in extremely small amounts in the atmosphere, approximately in the following proportions: helium, 1 part in 245,300 parts by volume; neon, 1 part in 80,800 parts by volume; krypton, 1 part in 20 millionths part by volume; xenon, 1 part in 170 millionths parts by volume. Many tons of liquefied air have since been systematically fractionated, but no other gas than those above named has been obtained. Julius Thomson, of Copenhagen, in a paper published in 1895 entitled "On the Probability of the Existence of a Group of Inactive Elements," pointed out, in relation to Mendeleeff's law of periodicity, that in periodic functions the change from negative to positive value, or the reverse, can take place only by a passage through zero or through infinity. In the first case the change is gradual, and in the second case it is sudden. The first case corresponds with the gradual change in electrical character with rising atomic weight in the separate series of the periodic system, and the second case corresponds with a passage from one series to the next. It therefore appears that the passage from one series to the next in the periodic system should take place through an element which is electrically indifferent. The valency of such an element would be zero, and therefore in this respect also it would represent a transitional stage in the passage from the univalent electronegative elements of the seventh to the univalent electropositive elements of the first group. This indicates the possible existence of a group of inactive elements with the atomic weights 4, 20, 36, 84, 132, numbers corresponding fairly closely with the atomic weights respectively of helium, neon, argon, krypton, and xenon. No discovery of recent years has created more widespread interest than that of the radioactive elements. In 1896, Henri Becquerel found that uranium salts emitted an invisible radiation which had the power of affecting a photographic plate, even though not directly exposed to it, exactly in the same way as the Röntgen or X-rays. Since that time, a number of substances have been shown to possess a similar property. Such substances are said to be radioactive. The radiation emitted by them is not uniform in character. It has been found to be of 3 distinct types, known respectively as the alpha, beta, and gamma radiations. The alpha rays consist of positively electrified particles moving with a velocity equal to about 1/15 of that of light. These rays have little penetrative power and are capable of being deflected by a magnet. The beta rays consist of negatively electrified particles of a mass not greater than 1/1000th of that of the hydrogen atom, and they move with a velocity approximating to that of light. The beta rays have a greater penetrative power than the alpha rays and are even more readily deflected by a magnet. The gamma rays are analogous to, if not identical with, the X or Röntgen rays. They move with the velocity of light, have a high penetrative power, but are not affected by the magnet. All 3 forms of radiation render gases electrically conductive, excite luminescence or fluorescence in certain substances, change the color of glass, convert oxygen into ozone, and yellow phosphorus into red phosphorus and act upon photographic plates. According to the disintegration theory of Rutherford and Soddy, the radioactive elements are forms of matter undergoing changes resulting in the formation of new forms possessing chemical and physical properties differing from those of the parent substance, these changes being accompanied by the production of sensible heat or some other manifestation of energy, due to the process of transformation of the changing atoms. The rate of change is found to be different for each radioactive element, but to be constant for the same element irrespective of its particular form of combination. The relative radioactivity of the various chemical combinations of a given radioactive element is directly proportional to the quantity of the element contained in them. The process of disintegration may be carried through a number of intermediate products until a stable form is produced. Uranium, in which the phenomenon of radioactivity was first perceived, is supposed to give rise to no fewer than 17 different forms of matter, including radium, actinium, and polonium. Thorium, another radioactive element, is supposed to disintegrate into 8 different forms of matter. Uranium disintegrates with extreme slowness. It is calculated that in a year, not more than 1/10,000,000th part of the uranium is transformed. The first disintegration product is termed uranium X. If a quantity of dehydrated uranium nitrate be treated with ordinary ether, a slight residue is obtained which is found to contain uranium X. It emits beta and gamma rays and is relatively rapidly transformed into other substances. Ordinary uranium, freed from uranium X, only emits alpha rays. Uranium salts can be freed from uranium X by repeated crystallization, uranium X remaining in the mother liquors. The existence of radium was first made known by Madame Curie in 1898. In examining certain uranium minerals and uranium products, Madame Curie observed that their radioactivity was apparently greater than that corresponding with the amount of uranium contained in them, and she was led to surmise that this might be due to the presence of some constituent more strongly radioactive than uranium. This supposition proved to be well founded, and she eventually succeeded in isolating a new element termed radium, forming compounds with characters and relationships akin to those of barium. The richest source of radium at present known consists of certain residues occurring at Joachimsthal in Bohemia, left after the extraction of uranium from pitchblende, in which radium occurs to the extent of 0.2 grams per ton. These residues are mainly sulfates of lead and calcium, mixed with a great variety of other metallic compounds. To obtain the radium, the mixture is heated with concentrated caustic soda solution, the residue washed with water and treated with hydrochloric acid, which dissolves the greater portion of the material. Nearly the whole of the radium is left in the insoluble portion. This, after washing with water, is boiled with a solution of sodium carbonate, so as to transform the alkali earths into carbonates. These are converted into chlorides or bromides, from which, by repeated crystallization, barium chloride or bromide is obtained, containing the greater portion of the radium as a halide salt. The radium and barium salts are then separated by fractional crystallization, the radium salts being slightly less soluble in water and alcohol and in solutions containing the halogen acid than the barium salt. Pure radium chloride, RaCl2, is a white crystalline salt resembling barium chloride, with which it appears to be isomorphous. Radium, like barium, forms an insoluble carbonate and sulfate, but a soluble nitrate and bromide. The bromide is much less stable than the chloride. On standing, it evolves bromine and becomes basic. Radium has, as yet, been obtained in such small quantities that very few of its compounds have been prepared. The rays from radium salts burn the skin and are found to be useful in the destruction of rodent ulcers. They appear to act upon proteids, destroy bacteria, bleach chlorophyll, and affect the germinative power of seeds. A pure and freshly prepared salt of radium seems to emit only alpha rays, but it soon forms disintegration products and then gives out, in addition, the beta and gamma rays. In the process of disintegration, the salts emit heat corresponding to about 75 gram calories per hour for each gram of radium present. Their temperature is thus uniformly higher than that of their environment. One product of the change probably connected with the emission of the alpha rays is the gas helium. Radium has an atomic weight of 226.5. It is regarded as a product of the disintegration of uranium, the atomic weight of which is 238.5. It is believed to have been formed through an intermediate product known as ionium, a radioactive element discovered by Boltwood in the mineral carnallite. The atomic weight of ionium is surmised to be about 230. Radium itself is supposed to form at least 8 disintegration products, the first of which is the so-called emanation discovered by Dorn in 1900, an inactive gas with an atomic weight of about 180, giving a bright line spectrum, decomposing into helium, liberating oxygen and hydrogen from water, and capable of being condensed to a liquid and solidified at a low temperature. Ramsay and Gray have determined its physical constants. The liquid is phosphorescent and shines with a color depending on the nature of the glass of the vessel which contains it. The solid is also phosphorescent, the color varying with the temperature. It gives out only alpha rays, and in its disintegration, like radium, evolves heat. Its position in the periodic table is probably above that of xenon. Other products are known as radio-lead and polonium. The latter substance was identified by Monsieur and Madame Curie in 1898 and was the first of the strongly radioactive substances to be recognized. In the periodic system, it seems to follow bismuth and to be a member of group 6, with a possible atomic weight of 210. Its spectroscopic characters have recently been examined by Madame Curie and de Bierne, who have shown that in its decay it evolves helium. The rate of disintegration of radium is relatively slow. It has been calculated that the time required for half of any given quantity of radium to change completely into other products is about 2,000 years. Rutherford has calculated that in 26,000 years a kilogram of radium would be reduced to 1 milligram of active substance, the remainder having passed into degradation products. In 1899, de Bierne announced the existence of another radioactive element contained in uranium minerals which he termed actinium. This is probably a disintegration product of uranium and identical with the imanium of Giesel. It occurs associated with the rare earths which can be separated from the pitchblende residues and is eventually found in the lanthanum salts. Nothing is known as to its atomic weight or its chemical relationships. It undergoes change and forms, apparently, a gaseous emanation which rapidly disintegrates and can be condensed to a liquid at a low temperature. 4 other successive products have been identified by the character of the radiation they emit, their degradation constants, and the time required for 1/2 of any given quantity to disintegrate into other forms of matter. Thorium was shown to contain a radioactive element by Madame Curie and Schmidt independently in 1898. Whether thorium is itself active is doubtful. The rate of disintegration of radiothorium is probably greater than that of uranium. It, too, seems to form a gaseous emanation which can be condensed at the temperature of liquid air, and appears to be an inert gas of high molecular weight, with the characteristics of the argon family. The type of radiation emitted by the several products has been observed, and their constants of change and half-value periods calculated, but little or nothing is known at present concerning their atomic weights, spectroscopic or chemical characters. End of Chapter 3.